recording now. The session is being recorded. Please be mindful and respectful of the class environment and your fellow students. Anything you say, type, draw will forever be recorded with your name attached to it. So just keep this top of mind and conduct yourself in a professional manner at all times. All right? Okay, so two things I want to discuss today. I want to get to to finish the discussion. There's one more revision, one more change to the sewer, the storm sewer, and then we can talk about the water main. Let me just make sure my camera's working in case I need to do a sketch. Okay, just a second. Okay, and one more thing here. Sorry. All right, so I have my, oops. Hang on, sorry, one more issue. Having some technical difficulties. And there we go. Okay. All right, so I'm going to share my screen. So my entire screen, allow. You should see my AutoCAD screen. Okay, just give me a quick yes or no in the chat there. Can you see me? You see my AutoCAD screen? Okay, so a couple of things to think about. These two grids have to have the same vertical exaggeration. Okay, so I think some of you may have had this at 5. I think this is wrong as well. The standard, if you look at it, let me just show you an existing drawing. Oops. So if we go to desktop, MED, downloaded file. So if we look at Ledger Way, you'll see the vertical exaggeration. So if you just go down to the scale, you can see here the vertical exaggeration, but the scale is here, 1 to 500 and 1 to 50. So that's a 10 times vertical exaggeration. So if you don't have that, you have to fix it. You want it all to be the same according to the standard. So you'll see this one here. This is Ledger Way. You don't have to do this to Ledger Way, but I'll show you how to do it. If you go to the Profile View Properties, and if you go, whoops, not Profile View, Profile View Style. And in this style, you'll see under under graph, whether this is 5 or 10. Okay, so just double check that it should be 10. Let me show you on the others. This is street A. And if I go style, under graph, this should see 10 times, right? So if this is 500, which is the drawing setting, what you see down here, then whatever you type here will automatically make this either 5 or 10 times. So it should be 10 times vertical exaggerated. Okay, so just double check yours, make sure they're vertically exaggerated by the correct amount. Okay. This here is also 5. If you make it 5, if you squash it, it's going to be the wrong one, right? So then it gets kind of flatter, right? So you don't want that. So I noticed some of you had 10 on one and 5 on the other. They should both be 10. So go to the style, because remember they're two different styles. One goes left to right and one goes right to left. So the settings are different for each one. Make sure they're the same. 10 times, okay? So remember this one, this view style, you'll list it. The view style for this one is road, and this one is road right to left. Okay, so just be mindful. Make sure that the vertical exaggeration is 10. Okay, just a quick housekeeping thing. So if you've designed all of the, let's take a quick look here. Here's the revision. So we did one revision so far. Let's look at the next one. So the first thing I did was once we had all our drainage areas, I added these backyards now to the mix, right? So to design this street pipe, I have this total area, which is this rear lot catch basin and this rear lot catch basin. And the area to each of those eventually get to this road catch basin. So what used to look like this, what used to be a drainage divide that looked like this, right? Remember, I drew this. These are the split points, and so on. And then in here, you'll see a high point, right? The 2%, 2.5%. So there used to be a split point here. So each catch basin, this catch basin and this catch basin, each had their own drainage area. But because we're not detailing the rear lot catch basin pipes on the design sheet, we're going to combine them. So I took the area for this one and the area for this one, and I combined it to the area for the pipe on the street. Because eventually these two backyard areas will combine to generate the flow expected in this pipe. Okay, so it's easier if you draw each individual area first and then add them together than to try and combine them. Okay, now if you can combine them directly, all the power to you. Okay, my brain doesn't work that way, so I always draw them separately. In this case too, when I draw them, I can also check that I don't exceed the maximum. Remember that calculation we did? What's the maximum area, so that we can always use a 250 pipe at 0.5%. Okay, so the first thing we did was that. The next thing we did was then amalgamate. So I know these backyards now are coming toward this street. So I got rid of this, this, and this. Whoops, sorry, this and this. So these three areas now combine to become this one area. The total tributary area that gets into this street sewer, this storm sewer. So I did that here, I did that here, and I did that here as well. Right? So there was one catch basin connected to this short pipe, and I combined it to what was happening on the street. Remember, the drainage divide used to be here, right? Used to do this, right? So this area and this little area combined to give me this total area now, okay? Because that backyard gets into that street pipe, okay? So that was the rationale. So when we did that, maybe these 2 or 3 pipes got a little bit bigger, and it may have influenced the whole system all the way to the end, because we're adding more flow to this entire leg of sewer. It doesn't affect these 2 pipes, but it would affect 1, 2, this little short 1, 3, 4, and the last couple pipes coming out. Okay, so that was a design revision when we realized I can't take these backyards to this road out here. It doesn't work. There's not enough capacity in this sewer system here. The next thing we need to look at, and we did this before, I'll show you again. When I designed my sewer, and we did this together, remember? Let's do the calculation again. If you take the closest corner, I'm talking about just these 4. There's 4 rear lot catch basins here. If you take these 4 rear lot catch basins, if you find the closest corner elevation and subtract 2 centimeters, so the 567 becomes 565, and then we go down to the invert by subtracting cover and by subtracting the pipe size. Okay, so it looks like this. Right, so I've got my top of catch basin, right? Wherever the closest corner is, I'm going to subtract 0.02. That's how I get my top. And then I go down to the top of the pipe. From the top to the top of the pipe, this is the obvert. I subtract 1.2 meters. And then from the obvert, I go down to the invert, and there's my pipe. It's a 250, so I subtract an additional 0.25. I have to do this in meters. And that'll give me the invert of the pipe. And we do that calculation actually at the center of the structure, right? From the center of the structure to the center of the structure. When we get to the street, we take it to wherever the center of the pipe is. That's a bad drawing. It should be bigger. All right, so the street pipe, I just extend, think about the center line of the pipe. I just extend this pipe until it hits that. And that's the length from the center of the structure to the center of the pipe. That's the total length. And it's a plane distance. It's horizontal, center line length. Okay, and then because it's a 0.5% pipe, I can calculate this invert. This is the invert at the main line. You need this invert and this invert for the contractor to build this pipe. Okay, this invert, can you please demonstrate how to calculate the lead invert at the catch basin located in the 3rd elbow? Yeah, I'm going to get to that. Let me just refresh your memory about this. This is typically how you do it all the time. So I am demonstrating it. If you know the top elevation, subtract 1.2, subtract the pipe size. That'll give you this invert inside. So now you have a top and an invert at the catch basin at the backyard, right? The rear lot catch basin. And then you go downhill 0.5% over this distance, whatever the length is. And that'll give you the invert at the main line. You do this 10 times. We have 10 rear lot catch basins. For the first 4 up at the top, so these 4 in the middle of the site, these 4, to get the top elevation, you take the closest corner and subtract 2 centimeters. Okay, and you go to the next one, you take the nearest corner, you subtract 2 centimeters. So this top will be 195.40, subtract 2, should be 3.8, and so on. Okay, so that's how you get the tops for these 4. The 6 along the south limit of the site, I already gave you the top. I gave you these numbers. These were all in the handout, right? If you want to see it again, there was a handout called, if we go to MED, and we look at this sketch here, this was provided, right? In this sketch, I tell you all those elevations, 552, 516, oops, and so on. So I gave you the top. You didn't have to adjust them by 2 centimeters. I gave you the tops directly. So all 6 of these, the tops were provided. So if you go back to this sketch, I gave you the top. Subtract 1.2, subtract 0.25, subtract the length times the distance in meters per meter. And that'll give you the invert elevation at all of the main lines. Okay, so this calculation you have to do 10 times. They're all independent of each other, but it's the same calculation. The tops are all different, but the cover and pipe size are all the same. The slopes are all the same, 0.5%, but the lengths might vary depending on how long or short the lot is. Okay? Okay, sir, how did you calculate P actual? Okay, we'll get to that question later. Okay, Daniel, ask me again. Let me finish this discussion. Okay. All right, so now that I have all those inverts, I'm going to calculate these inverts, right? So I'm going to take this 552, subtract 1.2, subtract 0.25, and then I'm going to take 40.1. Is it 40.1? Let me check, list this. It's 40.1 meters. This is the one down here. I'm going to go down 40.1 meters at 0.5% to get this elevation here. Then I'm going to project that. So let me change my UCS. And I'm going to project it. How do you do that? You go to your profile, the object to profile view. So I'm going to take that. So this is just an AutoCAD point. Make sure the description is not FG, because you don't want it on your finished ground surface, right? So this is got a different description, not FG. So I'm going to project it. And I'm going to put it in the profile and just use the elevation. You've already typed it in. And wherever that spot comes in, you're going to put in this ellipse, okay, with that invert. Okay, so you got to type in all these numbers. So once you've done that, then you can identify this is the pipe coming to the main sewer. It has to be above the invert of the pipe. So if I make a copy of this, if it comes in too low, that's no good. Higher is okay. Whoops, higher is okay. But it can't be too low, okay? Can't be below the invert of the pipe. So this one's okay. As a matter of fact, if you look at street A, when you do that for street A, you'll always be above. This one's above the pipe. 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 So they all work out on street A. On street B, once you do all 10 calculations and you project the points that you put in. So again, if you calculate, if you take the top of pipe, which in this case is, let me just turn this off, there's a lot of noise here. If you take 194.11, you subtract 1.2, you subtract 0.25, and then you subtract 38.7 times 0.5%, you're going to get this number here, 247. I'm going to project that to the profile, street B profile. So I'm going to put it on street B, accept the elevation, and there it is. So if I zoom in there, if I zoom in where this point came in, you'll see this is the pipe that's coming from the backyard. Notice it's lower than the street. As a matter of fact, when you do all these calculations on street B, the first one's okay. It's higher than the bottom of the pipe. The next one is just a little bit too low. That's a problem. And the next 4 are all below. This is the bottom of the pipe. That's too low. This is the bottom of the pipe. That's too low. This is the bottom of the pipe. That's too low. And the worst case is this one. Look how low this one is compared to the pipe you're trying to fall into. This is the corner one. Okay, this is the corner one. So if you look at the site, it's this is the culprit. This is the longest lead. It goes down the deepest. Okay, and it'll be between those 2 maintenance holes. It's connecting to the short pipe. So you'll see here it's between these 2 maintenance holes. and it's way too low. So how do we deal with this? There's two things we can do to improve this situation. Okay, so now that we've projected all of the main lines, right? Let's go back to my drawing. Right, now I know all of these inverts and I drew them in each road profile, 4 on street A, 6 on street B. So now I know where they are. There's two things I can do. The first thing is I want to lower this pipe. I want to lower the pipe of the design. Now to do that, I have to make them flatter, and I'm fixed at the beginning. So remember street A, this 825 exists, so I can't change it. Okay, but what I can do is flatten this pipe and flatten this pipe to the first intersection. I'm going to leave these two pipes on street A exactly as they are, okay? But I'm going to flatten this pipe and flatten this pipe. And when I get to the intersection, which is the end of street B, I'm going to flatten this pipe, I'm going to flatten this pipe, and I'm going to flatten this pipe. Sorry, no, I'm going to leave that one alone. You'll see why. Okay, so in the plan view, what does that look like? Let me show you. So let's look at the sewer system with the rear lot catch basin leads. Okay, so in this sewer system, this existing 825, I'm going to leave it alone. I want to make this one flatter. I want to make this one flatter. I want to make this pipe flatter, and I want to make this pipe flatter. Okay, and by doing that, it's going to lower the system. I'll be able to lower these two pipes. Okay, so let's look at it hydraulically now. I'm going to go to my design sheet. So I'm going to go to my design sheet, my storm sewer design sheet. Okay, can everybody see that? Just make sure. Can everybody see my spreadsheet? Okay, so here's the original design that I've already drafted. All the pipes are at 0.5%. What I want to do is flatten the first two pipes, right? This is the existing one on street A. I want to make these two flatter. Okay, I'm allowed to go as flat as 0.25%. Okay, and how do I know that? It's in the standard. So let's look at the standard. If you go to the town of Milton and you go to the pipe standards for storm, it's going to tell me, where is it here? Hang on. Okay, so in here, it's going to tell me that I can flatten the pipe. Here we go. So in no case shall the gradient be less than 0.5%, right? Which is typically parallel to the flattest road. For pipes less than 600. Okay, so if you have a 600 pipe or smaller, it has to be at least 0.5%. When you get to a 600 or bigger, right, or sorry, bigger than 600, then you can put in a 0.25% pipe. So if the pipe gets bigger, then you can flatten it to 0.25. Okay, so let's look at our spreadsheet. That's where I'm getting my 0.25 from. So if I go to the spreadsheet, right, this is already a 675 pipe. Right, this is already a 6. So I'm going to flatten this one, 0.25. I'm going to flatten this one, 0.25. And I'm going to flatten the first two pipes on street B. This one, 0.25, and this one, 0.25. Okay, now when you flatten the pipes, you have to redesign them and always start at the top and work your way down. If I make this flatter, is this big enough? Well, look at the percent full. It's a little too tight. It should be less than 85%. Not only that, I can't have anything bigger than, it has to be at least a 600 pipe. 600. That's already cutting it close because it says greater than 600, but I'm going to push it to 600. And now I have the capacity back. So I made it flatter and I made the pipe bigger. The next one has to be the same size or bigger. So I'll make it a 600. 72, that works. And when I get to the end, you'll see this is almost full. That's too small. So I'm going to make that one the next pipe size bigger, 750. And then the next one, 750. So I've changed these two pipes, size and slope, and these two pipes, size and slope. That's the revision I made. Now I'm going to take advantage of the flatter pipe, okay? And I'm going to recalculate all my inverts for those pipes. All right, so if you think about this, we'll go back to the drawing. Oops, go back to the drawing. Turn everything on. If I go to street A, right, this one we're going to leave it alone. I'm going to make this pipe size bigger. It's a 675. I want it to be a 750. Now I'm going to answer a question that I've been getting from some students. I can't change the pipe size. Watch this. I'll show you. show you how to do that. This was a few questions I had from some students. Okay, let me just move this out of the way. Okay, so I want to change this 675 to a 750. Okay, so I'm going to click on it, right click. I want to swap the part, and I want to choose the 750 pipe, which is a concrete pipe, 750. When I click on it and say OK, it doesn't change. Okay, if people had this problem, you can't swap the part. Give me a yes or no in the chat. If people had a problem switching the pipe size, especially the bigger ones. Okay, so here's how you fix it. Okay, here's how you fix it. Ready? Pay attention. So if you can't swap the part, which is really what you want to do, that's the command, here's a solution. This isn't the answer to the question, why doesn't it swap? I don't know why it doesn't swap, but here's what you can do about it. So you can, instead of swapping the pipe, go to the pipe property. Same command you use to update the inverts, right? If you scroll down to the bottom, you can choose the pipe size from this list. And all the bigger pipe sizes are here. So I have a 675, I want a 750. So that'll change the size of the pipe. And because it's a concrete pipe, and it might say PVC, you can change the material here. Now, if the material's not listed, you could just type it in, CONC. Okay, so you can choose the pipe size from this list, or swap. If swap doesn't work, this is the solution, the workaround. And then you can type in the new material. So watch what happens now. When I say OK, the pipe size and the material should change. Say OK, and the size changes. Okay, let's do the next one. This one, swap the part, make it a 750, say OK, doesn't do it. Okay, so here's what I'm going to do instead. Click on the pipe, right click, go to pipe properties, scroll all the way down to the bottom and select the size from the list, 750. And if the concrete is not there and you can't choose it from the list, you can just type it in. Okay, and there's your 750 pipe and so on. So once you change the pipe size, and you have access to that in the profile, yeah, you can actually do that in the profile. If we go to Street A, right, I can actually change the pipe size here. I can use the swap command if it works. It doesn't always work. Actually, it might not be here. The swap command's not here. But you can go to the pipe property and change the size here. Right, as long as you're just accessing the database. So if I want to make this a 600 again, the pipe will actually get drafted smaller. See how it's smaller? It keeps the invert and it lowers the top of the obvert. Okay, so let's change it back. Pipe properties. Let's make it a 750. Say OK. Now, the pipes are bigger, but what am I really trying to do? I'm trying to make it flatter. So I'm going to take this pipe, right click, go to pipe properties. I'm going to keep the end. Yeah, I typed in concrete. You can't choose it if it's not on the list. Okay, so I'm going to keep the end. So I'm going to change this to 0.25. When I say apply, watch what happens to the graphic. This edge is going to come down. Right? So the pipe got flatter. Now I'm going to go to the next pipe with the start. The start of this pipe, copy, say OK. These pipe sizes are the same, and it's about a 45-degree angle, so the drop is 5 centimeters. So I'm going to take this, pipe properties, paste this into the end, and raise it by 5 centimeters, so 99 in my case. These numbers might not apply to you. It depends where you drew your maintenance holes. Say OK. The pipe goes down, and then right-click, go back to properties, and then change it to 0.25. Say apply, say OK, and now the pipe is lower. Okay, now I'm going to take that invert and I'm going to go to the other side, and you'll see this outgoing pipe. The outgoing pipe is lower. I can now match obverts if I have to, right? So if I know that pipe size, this is a 750, and I'm connecting this pipe size is now a 600, so I have to change the size. Pipe properties. Will it let me swap? Let me see. Swap pipe. Oh, I can only swap pipe in the plan view. So I want to change this one. Swap part. I want a 600. Say that actually works. I don't know why the concrete ones aren't behaving. And the next one wants to be a 600. Swap part and make it a 600 as well, and flatten them both. So I'm going to do the invert work in the profile. Right, so the pipe got bigger, 600 and 600. So what am I going to do now? I'm going to take the invert of this pipe here, the one I'm connecting to, pipe property. I'm going to take the start of this pipe, copy. The difference in pipe size, a 750 and a 600 is 0.15. For a 90-degree bend, I only need 0.8, so 1.5, the difference in pipe size governs. So I'm going to add to the start of the previous pipe to get the end. So I'm going to take this. There's the start of the previous pipe. I'm going to add 15 centimeters. So 7 plus 15 is 22. Say OK. And now the obverts match. And then I can flatten the pipe properties, and make it a 0.25, holding the end. Apply. Watch what happens at this end here. It's going to go way down. Apply. And I'm pushing the pipe down as much as possible. Okay? So through the magic of television, I've already done this. Okay? So once you lower the system and recalculate your inverts for the flatter pipes, this entire system, these two pipes are going to be bigger but flatter, lower, and then that'll continue up into this street B. So let me show you what I've done. I don't want to do all the math. I think you get what I'm talking about. So here's what it looks like. Here's what I did. On street A, I made this one a 750 at 0.25%. I made this one a 750 at 0.25%. I recalculated the inverts with minimum drop, and then I started street B, and I did the same thing here. Right? I took this pipe, and it's now a 600 at 0.25%, and this short pipe is a 600 at 0.25%. And the next pipe, I left it alone. It's still a 450 at half. It's still a 4, and this is still a 375 at 0.5%. But again, I did minimum drop, minimum slope all the way along. Okay? So if we go back to the original, I'm just going to flip between two files. Don't do this. Revise one file only. I just did this so that I didn't have to, so that I could show you the end result quicker. So what I did is I have minimum drop, minimum slope, minimum drop, minimum slope. And I lowered, so now I was able to lower this pipe, right, to match this. It doesn't have to be all the way up here. So this ended up coming down as well. And then this one ended up coming down, and the last pipe came down as well, okay? So without redoing everything here, I'll just show you what the result was, right? This purple line, this magenta line, those are the original pipes before I made this revision, the 0.5% pipes with the other sizes. So here's where the sewer used to be, and I've pushed it down by about 1 foot. Now, it doesn't sound like much, 1 foot, but it's significant because I'm trying to get down as low as possible, okay? So that's the revision you make, okay? Let me describe it one more time. Okay, so let me just take this and this again. So we're gonna make this pipe, and this pipe, and this pipe. These 4 pipes, right? Your design pipes, 1, 2, 3, and 4. We're gonna make them 0.25%, flatten them. And that will drive the sewer system down, much lower, okay? Once you do that, recalculate all the inverts for all the pipes. 1, 2, 3, 4, and recalculate these with minimum drop as well, but keep them at 0.5%. So they'll get pushed down because the first 4 pipes are lower now. Okay, so these just are a vertical shift straight down. They're still 0.5%. So that's the revision. When you do that and you review, remember my catch basins from the backyard? Let's see how they relate. Is the pipe now deep enough to capture that? Okay, let's review it again over here. Let me undo a few steps. Let's look at it before the revision. Okay, so here's the original design, right? So remember, street A works, no problem. On street B, the first one works. The next one doesn't work by just a little bit. It's a little bit too low. And the rest of them don't work. That's too low, that's too low, that's too low. This is definitely a problem, right? So 5 out of the 6 are no good. Now that I've pushed the sewer system down, let's see if I've resolved any of those. So 5 are no good. Let's see how many are fixed now. So the pipe is lower, right? So the pipe used to be up here, and now it's way down here. So this is good. It always was. The next one didn't work by just a little bit, but now it's way above the invert of this pipe. So that one works. So I've resolved one of the issues. The next one, I've resolved that one as well. Now it's inside the pipe instead of below this pipe. So that one works. The next one used to be below the pipe. I'm just drawing this for reference, and now it's inside the pipe, so that's good. So I've resolved 1, 2, 3. The next 2 are still no good. Here's where the pipe went. It went from up here, it used to be up here, and I shifted it. It's now down here. It's better, but it's still too high. This is still too high. And then the last one down here between that short pipe, the pipe used to be way up here, and we've shifted it to be down here. We've actually made it bigger and flatter, okay? So we have gotten some depth, but you'll notice it's still too high. It used to be up here, and now it's down here, but it's still too high for this one. So of the 5, 3 of them are better now. The last 2, these 2 here, are still a problem. So now there's one more technique we can make use of, okay? And here's what we're gonna do. Okay, any questions so far? What we're doing or why we're doing it? Okay, so I've improved the situation, but I haven't solved all my problems. I solved, of the 5, I solved 3 of them. Okay, so just remember, if you make the pipe flatter so that you can go deeper, you might have to make the pipe bigger. Okay, and that's why there's a little bit of back and forth. You have to change the geometry. I'm changing the slope because of my invert design. I have to go update that in my spreadsheet. And when I change the slope because of my invert issue, I might have to change the size. If I change the size in the spreadsheet, I have to update the size in the drawing. So it's back and forth, back and forth. It's a bit of an iterative process. And that's the nature of it. And if you don't like what I'm showing you, then you're in the wrong business, because that's just the nature of the work. Okay, so that's just the reality of the type of work you're going to get involved in. So it's always a bit of back and forth. Do some work, advance the design. Something's not making sense. Okay, go back and what can you do different to try and fix the last problem you just uncovered, and so on. So one thing I did to fix that problem that I uncovered, these backyards from the south limit of the site not being high enough, is to flatten the sewer. Okay, and I made use of that absolute minimum 0.25. Now I'm stretching it a little bit. If we go back to the standard, it says any pipe less than 600, right? The gradient must be, in no case shall the gradient be less than a half for pipes less than 600. In the diameter, if you can use a quarter pipe for greater than 600. So it says less than 600 and greater than 600. It doesn't tell me what to do with a 600 pipe. I'm going to assume it's the flatter version, okay? In no case shall the gradient be less than a half for pipes less than 600. So that's a 525 and smaller. And 0.25 for a pipe greater than 600. So it really, that statement doesn't tell you what to do exactly with a 600 millimeter pipe. Okay, so I'm going to assume it's in my favor. I'm going to allow 0.25 on a 600. And that's what I did. Okay, it might come back that I have to make all these flat 0.25 pipes at least 675, the next size up. Okay? But I'll know after the town reviews it. So I'm just gonna put it in my favor. I'll use the smaller pipe for the flat, the 600 instead of 675. Okay, so now what else can I do? What else can I do? Well, now I have no choice but to raise these. When you raise these, what you're actually doing, let's go back to my drawing. Okay, so here's what we've done so far. I have a catch basin in the backyard. I have a pipe going to the street, right? It's calculated to the center. And then the street sewer, at the center line of the street sewer, the pipe's up here. Well, that's no good. So now I said, okay, I'm going to flatten the sewer. So instead of 0.5%, on some of the pipes, I used 0.25%. So now it took the design of the sewer, it made it bigger, but lower. So now what used to be the problem here relative to this is now this relative to this. Okay? So I've improved the situation by using a flatter gradient that's allowed. But now this pipe is still too low. So what do? We take this pipe and we raise the whole thing. We keep the slope, 0.5%. We keep the 0.5% and we raise it. And what do? As a minimum, we have to match this obvert. So I'll take this invert line and start here at the invert, match inverts, and make it parallel. Just shift it straight up. So what used to be here is now here. I've raised it straight up. I keep the 0.5%. I'm going to keep it at 0.5%. Okay. So now I've compromised the cover. Remember the cover? I'm cheating on the cover. The cover used to go from the top to the invert. Remember, this was 1.2 and 0.25. Okay. When you push the pipe up, you compromise the cover. The distance from the finished ground to the top of the pipe is now less. This is going to be less than 1.2. Okay? By how much? Well, we're about to find out. Okay, so that's what I'm going to do. So by how much do I have to raise it up? I need to take, and let me get rid of this reference pipe. right? We're changing it. It's no longer there. I just brought that in for visual reference so you can see where the pipe used to be. Okay, this is where it is now. It's flatter. So I'm still too low. I'm going to draw a line from the node straight up. And you can't trim against an object for some reason. It won't let you, so I have to trace it. It'll let me snap to it, but it won't let me use it as a cutting edge. So I'm just going to trim it here. Okay, and I'm going to take that to the invert. Okay, I need to raise this invert from here up to here. So this is the vertical shift. Okay, now when you draw this, remember it's 10 times vertically exaggerated. So whatever this says, divide by 10. So I'm going to list this. I'm going to divide by 10. So it says 665. It's actually 0.665. So I have to raise it by 0.665. Okay, 0.665. Let me go back to here. So this now, from here, from the bottom of the invert to the bottom of this invert to match here, right? I'm doing the same vertical shift. This distance and this distance is the same. I need to raise it by 0.665. And that compromises cover by that much. So what used to be 1.2 is now almost half, right? A little less than half. Okay? So when you do that, sorry, let me turn off my notification. Okay, sorry about that. Okay. Oh, geez, sorry. Okay, so when you do that, then you can shift the pipe, and now you have at least the flow you need. Okay? You have the flow you need. Okay, but the cover is compromised. How do we deal with the cover? That's a separate issue. I'll show you that in a minute. So what do you do now? Now you kind of reverse engineer it. I'm going to make a copy of this from here over to here. So that's where I want it to be as a minimum. Okay, you can go higher, but the higher you go, the less cover you're going to provide. Okay, so you have to worry about cover. So only raise it the minimum amount. So this is the height you want to go up by. Okay, so we know it's 0.665. So now what do? Now you start at the main line. Now you design. Now you know the elevation here. Let me use a different color. Now you know the elevation here. You're going to go up 0.5%. You're going to go up 0.5%. Sorry, you're going to go up 0.5%. And you're going to recalculate the invert inside the pipe. And now you have the top. That doesn't change. The invert in the structure, this changes. You have to update this number. So whatever the vertical shift is, if you take this invert and you raise it to here, right, and you take this invert and you raise it to here, you know from here you want to go up to here. So that's how you get the vertical shift, 0.665. So you know how high to make it. You get that invert, you go up at 0.5%, and you calculate the invert here, and that's the new invert at the structure. And then the pipe is still underground, it just doesn't have frost protection. Okay, and how do we deal with frost protection? I'll show you that in a minute. Okay, so here's how you deal with that. Any questions about this technique? Raising the rear lot catch basin lead to match the mainline pipe. That's really what we're doing. Okay. All right. Any questions about this? So if you follow the instructions, these two techniques, flatten the pipes that I suggested, and then you should have problems with only these last two, the ones in the southeast corner. You should be able to update this. Okay, so you have to do this once here. This is the worst one. And then this one here. Draw a line from the quad here, take it up, trim it here. So this is the vertical shift. You have to raise this invert, whatever you calculated, by this much. And remember, whenever you list this, you have to divide by 10. So it's only 0.105, about 4 inches. Okay, so these two need to be adjusted that way. Recalculate the invert here, and then work backwards, right? You know the elevation now, the new elevation at the street, at this end, go up at 0.5% and recalculate the invert here. And you'll know the difference between this number and this number does not have enough cover. So we only need to change to it. If your design is similar to mine, and it should be, those are the only two that are going to be adjusted without enough cover. Okay, so there should only be two, and it'll be this rear lot catch basin here, this one here in the corner, this one here, and the next one over, this one. Okay, these are the only two that need to have this vertical shift. You have to raise these pipes through the side yard so that you have proper drainage. The rest of them will take care of themselves just with the flattening of the pipe. Okay, Tron? Now, why is it that I can get away with not enough cover? Okay, and here's the technique. Now, we're not going to detail this, but I just want you to know this is possible. This is something you would have to put on your design if you were to do this. So if you look at the cross-section of the pipe, right, look at it sideways. So I want to see the end of the pipe. If the original, let me draw it again here. So if we take a cross-section through the side yard, right? So I'm going to draw, as an example, I'm going to draw a line across here. So I'm going to draw a line. I want to look at the cross-section of the pipe. Okay, there's the pipe. So I want to look at this cross-section. So it should look like a circle, right? When we look at this pipe in section. So here's what it looks like. So the pipe is usually, here's a different color. Here's the pipe. Here's the finished ground, right? Finished ground. And from the finished ground to the top of the pipe, we need 1.2 meters, okay? And then what's really happening is when you design this pipe, there's bedding, so there's some granular material. This is usually a granular. And then there's cover on top. This is usually a sand layer. So if you look at any trench cross-section, this is granular, and this is sand, and then there's native fill on top, okay? That's generally how it's done. So you would excavate, depending on the soil type, you would excavate down to this level, and then you would have, I think it's about 6 inches or a foot here. You would put in this granular to cradle the pipe. This is called the bedding of the pipe. And then you would put sand on top. The sand acts like a cushion so that when you put in your native material, it might have rocks and so on. It protects the pipe from getting damaged. This is what your typical trench looks like. But the cover, again, from the finished ground to the top of the pipe, from the finished ground to the top of the pipe, that has to be 1.2. Now, when we compromise that, here's what happens. I'm going to take this and I'm going to shift it up here. Now I no longer have cover. Okay, so what do? Usually, not always, but usually the rear lot catch basin lead, instead of using granular and sand, sometimes they insist that instead of granular and sand, this is a typical street sewer, but when you go between two houses, they don't want you to use granular and they don't want you to use sand. They want to concrete encase the pipe, make it all concrete. Okay, so that's another option, and I believe that's covered in the standard. So if we look at rear lot catch basin leads, let's look here. There might be some language about that. Leads in the allowance, rear catch basin to be sumpless, right here. The rear lot catch basins are sumpless, any sump filled with a mass of concrete, okay, ditch inlets. Is there any here about concrete encasing? Road catch basins, part of it has to be concrete encased to the first joint. Now, if you look at rear yards, they usually tell you the whole thing needs to be concrete encased. Let me just look at one more. Road catch basins, backfilled. The first joint of a rear lot catch basin is to be concrete encased. If concrete pipe is used or fully concrete encased from the catch basin to the private property line. So what they're saying is they want you to protect the pipe by pouring concrete from the street line all the way to the structure. So basically, from here to here, they want you to put the pipe inside concrete. Okay. On the street, it's typically the sand and gravel. So if you're going to put concrete, here's the trick. If you're going to put concrete here, right, and this point here is frost protected, it's way below the frost line. What we do is, because we have to concrete encase this, there would be the top of the concrete and typically the bottom of the concrete. But instead of building it up there, we do this. We put concrete all the way down to the original depth. So what used to look like concrete like this with a hole is now a higher hole, but the concrete encasing still goes down to the original level. Okay, let me show you that. Right, so here's the original hole down at the regular level. We concrete encase the whole thing, so the bottom is here. If we raise the hole, if we raise the pipe, we don't raise the bottom of the concrete. So now what you have is a block where the bottom is well below the frost. And that's the trick in being able to not have cover. This is less than 1.2, right? It's less than 1.2, but really frost can't act. And the problem with frost is when the ground freezes, water expands and it pushes things up, right? So if water gets underneath this and expands, it'll move the pipe up and down. So it'll freeze and then thaw and then freeze and then thaw. If this is always below 1.2 meters cover, it never freezes. It's frost protected. Okay? So the thing is, if you're going to lift this block of concrete, it's hard to grab it from the sides and push it up. You really need to get underneath it. You have to get underneath it to push it. Well, if you prevent freezing underneath it, then you're frost protected. So even though the pipe is below frost protection, the structure that it's encased in is below the frost level. So this might have freezing in the sides, but never underneath. And really, when we talk about frost protection, they talk about to the obvert, right? Make sure there's no frost here. Really, frost protection can go to the spring line of the pipe because it's not until you get underneath the pipe, right, that you actually start to affect the movement of it. So this is conservative, okay? But again, if you frost protect all the way to the bottom, then it's even better. So this is the trick that's played. When you have substandard cover, you regain the frost protection by making the concrete encasement deeper. Okay. Now we're not going to detail that, but that's something that's possible. As long as the pipe is underground, you can always concrete encase it. And I've done this. I did this on a project once where I had to raise the rear lot catch basin about a foot, 0.3 meters below the finished ground. It was just under the ground. It was so tight, and I got permission to do that. 0.3. This was in Richmond Hill a few years back. So in combination, the two techniques, again, are flatten the pipe as much as you can. So I use the 0.25 instead of the standard 0.5%. And then the ones that are still misbehaving, I raise them. And that's the calculation you need to perform. Okay, so then in the profile, you'll eventually see this. Instead of this pipe down here, right, it'll be up here. And instead of this pipe down here, it'll be here. And you have to retype the inverts, recalculate the inverts at the back of the lot where the catch basin is. And that's the final solution and the concept. Again, the numbers, the inverts are going to vary. They're going to be different for every student depending on how you drew your pipes. Okay? Any questions about that technique? Okay, and I deliberately rolled it out a little bit at a time, right? Start with the standard, right? Start with the standard, 0.5%. So you're designing the storm from the bottom up, right? Let's just do this one concept here, right? The storm is being designed, right? The existing pipe is here. There's the 825. Then there's the shift. Then there's this. There's street A and B. We're coming down here. We're coming down here. One more here, and then two more up here. So that's the system. We design them all parallel to the street. The street is 0.5%. These pipes are all 0.5%, which is the minimum allowed. Okay. Then we come back and we can draw that. We can find out what those sizes are when they're all 0.5%. We can get our design sheet ready. We can draft all these pipes in the profile view. Then, so we start from the bottom and work our way up. Then we start at the back. Then we stop that design and we start at the back with the catch basin and come down, right? So we designed going uphill. And then we start at the backyard and we design going downhill, and then we check what's happening at these points here. If this is too low, we have to find a way of driving the sewer system down or raising this pipe up. And the two pipes in the corner, this one and this one, require a little bit of both. I have to flatten the system. Which pipes are we flattening? We're flattening 1, 2, 3, 4. Those are the ones that are going to be 0.25%. And then we're going to recalculate all the inverts from here all the way to here and all the way to the end of the site. We're pushing this whole system down even though these two don't change slope. These are still 0.5%. This one's still 0.5%. When you do that, you'll fix most of the issues, except for these last two on the southeast corner. Then these, we have to raise them up to match. And that's the last fix. So it's a combination of pushing the sewer down and raising the Riolat catch basin leads up. And that'll be a solution that'll work, together with that frost protection. Okay, don't worry about detailing the frost protection, just get the inverts of the pipes correct and show it properly in profile. Okay, and then you'll still have your sanitary sewer and everything else, right? Like you still have a sanitary sewer. You're drawing both your SAN and your storm together, right? Sanitary and storm together. You have to label all the pipes, label all the maintenance holes, right? So I've got pipe labels. Now I need all the maintenance hole labels and so on. And then there's a bit of drafting to do. Make sure they're not overlapping each other. Just like we did in CDA last semester, if you remember from CDA, those of you who took it last semester. Any questions about that design? Okay, so if you look at the, what should we do with the profiles, labels at the street, existing connection. There isn't enough room. Well, make room. You got to make room. You're talking about street A. To get street A to work. So what you can do with, there's some tips and tricks, if you will, right? If you go to the profile properties, you can change the specified height. You can add some height to the grid, right? So make this line higher. So make it 200. And now you have some spaces to put labels up here. And if you want, you can lower the bottom too. Instead of starting at 190, you can go to pipe profile, profile properties. Instead of starting at 190, you can go down maybe 2 meters, 188, and have some room underneath. The horizontal size, do your best. And if you need a leader to point to it, then that's what you have to do. Okay, so I'm going to leave that up to you. Yeah, you can put the label above, for sure. Yeah, just make sure there's no overlap. Okay, so do your best. It's your time to shine. You have to figure that out. I recognize the problem, but you have to figure that out. That's a good question, Stephen. Yeah, but that's part of the requirement. You got to figure that out. Now, watch, and this leads us into the next thing. Okay. Any other questions about storm? Okay. We also have a shopping list here of stuff you need to do. So if we go back to, I posted this. It's online under the project requirements. So if we go to MED, there are submission 3 tasks. I gave you this list, and I think I discussed them all. Water main is next. I'm going to do that right now. Okay, so give me a minute. We'll get to that one. The top of maintenance hole 301 are sticking out of the road profile. What should we do? How far is it? By a little bit or a lot? Talking about street A or B? Samuel, A or B? Street A at the intersection right here? This thing? Yeah, the reason that's happening is because of the road surface. So I'll show you why, okay? And then you can decide how to fix it. Let me turn off these labels. There's a lot in the way here. And let me turn off these labels. Let me show you my road surface. So my roads, I'll bring in my road surface. So this is why these maintenance holes are okay. These ones appear to be in the boulevard of street A. Let me hang on. Let me show you with my. Let me show you with the corridor model. Let me turn on my corridor model. So if we look at the corridor model, these 2 maintenance holes, this one and this one, are actually in the profile of Ledger Way. Do you see that? The profile of Ledger Way. It's in the boulevard, which is not the pavement. Notice street A stops right here. You see that? That's why. So the elevation of these 2 look like they're higher because the elevation on the road model is actually the boulevard of Ledger Way. Okay, the only way to fix that, this is what I would do. The only way to fix that is if you turn Ledger Way off. So you can turn Ledger Way off. But then it causes another problem. Let me show you. If you take this, if we took the corridor model and we turn ledger way, if I turn ledger way off, okay, that's gone now. Now these two don't have an elevation because there's no surface out there. Okay, let me turn my surface back on. Right, now the surface doesn't go far enough. Look, watch it. If I take this and these two, object, whoops, these two, object viewer, right, they're outside the range of the surface. Okay, if you zoom in there, they're outside the range of the surface. So now they don't know what to do. So now what you can do is take this and stretch it forward. And now they're in range. Right? You don't want to go all the way to the end, but somewhere over here. Now they're in range, and it still might look off because you're technically, you could be in the boulevard. You're on the curve. So this one is going to appear higher than this one by quite a bit. Let's take a look at it in the profile. Street A, right? One of them is still higher because it's in the curb of the projected road. Okay. So these are the little tricks that you kind of have to play with. If you don't want to deal with that, if you don't want to make the surface perfect so that the manholes come out correct, just do this. Watch, I'm going to undo all my revisions. I'm going to bring ledger way back. So do you understand why they're too high, right? They're actually in the boulevard, not in the pavement. So they're higher. So this is the simplest thing to do. Just take these and just grip edit them down. That's all you need to do. You know they're down below. Samuel, does that answer your question? Just adjust them manually. Okay, and just eyeball it. It'll be close enough. Okay? They should all be close to or just below the road. Okay? It could be above by a little bit, but mostly it's below. So that's what I would do. If you wanted to, the correct digital thing to do would be to actually model this intersection correctly so that this asphalt is correctly represented. I'm not going to get into those details right now. Okay, what to do that is a lot more new alignments and new targeting requirements. Okay, but it's more work than it's worth. I would just grip edit them down, make them look like they're supposed to. Okay. All right. So when you draw this information, this is all AutoCAD, right? You need these rear lot catch basin information. This stuff, this is all AutoCAD. Okay, so watch what happens. If I move the grid, the profile view, watch, if I move it, that stuff doesn't go anywhere. I drew it there. It's not connected to the database. These pipes are drafted in this profile view. So when I move the view, anything drafted by Civil 3D goes with it. Anything that you drew in AutoCAD is static. It doesn't go. Now you can move them together by selecting everything, move everything, and then you can move everything together. But technically it's not part of Civil 3D, right? If I move the Civil 3D grid, only the Civil 3D things connected to it will move. Okay? Everybody understand that? So keep that in mind. Once you place this, right, you want to try your best not to move it. And here's the other danger. Remember, if you change the bottom elevation, see where these are? Watch. If I change the bottom elevation from 190 to 189, if I take a meter off the bottom, so if I manually change this, if I go down 1 meter, 189, watch what happens. The blue stuff at the bottom doesn't move. It pushes everything up. See that? But now these are in the wrong spot because they're not part of the database. So now I have to manually adjust them. I have to take these things, these manually drafted things, right? Take this and this and this and this, and I have to push them up by a meter, a vertical meter, so I can use this as a reference. Endpoint to endpoint, which really is 10 meters. And there it is back in the right spot. Okay, so just be mindful. You can raise the grid, you can raise the top, but if you lower the bottom, you might have to make that adjustment. So if I go to Profile Properties, I can raise the top. I can add to this 200. It doesn't change that. This is fixed. The insertion point of the grid, this thing is fixed. So if you add to the bottom, it pushes everything up. Okay, you can add to the top, but you can't lower the bottom or change the bottom, right? So if we go back to this is automatic and say, okay, Now it looks funny, so then you got to move those things back to where they belong. And it's typically a vertical shift of a meter or two, whatever your change is with the bottom number. Okay, does everybody see that behavior? It's important because it's going to come up again when we do the water main, which I'm about to show you. All right, so these have to go down by a meter, so from 5 to 4, and now they're back where they're supposed to be. So just be mindful that when you draw something using AutoCAD, it's not part of your database, it's static. So if you make changes to the data, you may have to adjust the profile. The other thing too is that when you draw these, remember this is vertically exaggerated 10 times. If I change the scale factor, if I go back to profile style, if I change this to 5, then these are all not only in the wrong spot, but too big. The top, this needs to look like half the size. It'll get squashed vertically, right? It'll get squashed vertically. So now you have to redraw that. So scale is a bigger problem than a shift up and down. Okay, so you have to make sure anything you draw manually, if you change the bottom elevation of your grid, or if you change the vertical exaggeration of your grid, you have to redraw anything you did manually. And that's a bit of a pain. Okay, so you want to establish scale and elevation. The vertical shift for changing the elevation of the bottom is not as difficult a task as changing the vertical scale, where you have to squash stuff or either stretch or squash stuff based on the new scale. So how do we draw the water main? Well, let's look at LedgerWay. There's a standard for it. It's written in the document. Where's LedgerWay? Sorry. Let's go back to LedgerWay. LedgerWay. So where is the water main? Okay, and this is in the Halton standards. The water main typically is parallel to the road. Right, so you can see the road here. The water main is parallel to the road for the most part, and typically it's 1.7 meters below. So frost protection on the water main is a little bit deeper than 1.2. It's 1.7. Because not only do you not want the pipe freezing, or the ground around the pipe freezing, but you don't want the water inside the pipe freezing. So you want to give it a little extra added protection. So the pipe is always parallel to the road, usually, not always, but usually it's 1.7 meters below the finished ground. So to draw the water main, trace the finished ground. So this is what I'm going to do. So here's how you draw your water main in profile. So I'm going to create a new layer for the water pipe, if it's not already there. Typically it's seawater profile. I'm going to make that current. I forget what the color is, blue or cyan. Blue, okay. I'm going to turn my O-snaps on, clear all to endpoint, and I'm just going to trace my finished ground. So just go to all the PVIs. This is the general shape of your water main. Okay, now you want to go straight down vertically. Don't offset. Do not use the offset command. If you offset, and remember this is 10 times vertically exaggerated, right? So I have to multiply by 10 when I go vertical. So if you offset 1.7, you're going to get this solution. Let me isolate this. Right? If I offset this 1.7, I'll get this solution. Sorry, not 1.7, 17. Multiply by 10. Offset 17, I get this solution. Or I can copy this straight down, turn your ortho on, 1.7 or 17. And you'll notice they're two different solutions. They're close, but they're different. When we talk about cover, it's a vertical thing. So it's not the offset, perpendicular. It's not this offset. I believe it's this one. This is the offset, 17 meters. I don't want on an angle like that, parallel. I want to go straight down, 1.7. This is what you want to do. Everyone likes the offset command, okay? But it's the wrong thing to do. When we talk about depth, it's always a vertical thing. When we talk about distance, it's always a horizontal thing. We never measure in 3D, okay? It's either horizontal or vertical. So the correct thing to do is make a copy of the finished road surface straight down 17 or 1.7 times 10. So there's the top of the water main. Okay, what's the size of our water main? The size of our water main? Well, the water main throughout the site is 200. Remember, we're going to use a 200 everywhere. So I'm going to make a copy of this 200, which is 0.2 times 10 is 2 meters. So there's the bottom of the water main. So there's the top of the water main, there's the bottom of the water main. And that's basically it. There's more to it, but that's the general idea. Okay, I'm showing it on street A. You have to do it on both streets, right? The proposed part of Chuchmak, street B, don't redraw the existing Chuchmak pipe. Just draw the new one here, okay? So there's the top and bottom of water main. Then you need to add the street furniture, right? So what kinds of items do we have in the plan view, right? Well, we have hydrants, we have valve chambers, and we have valve boxes. So the best way to do this is with AutoCAD points, using a technique of projection, just like we did before. So what objects do we have? Well, I'm going to draw an AutoCAD point. I'm going to put it here in the center. There's the center of my valve chamber. And I'm going to move along the water main. Oh, here's a hydrant. Center. There's where my hydrant is. Oh, here's a valve box. Center. Good. Here's, I'm going to use this one. I drew two because I wanted to check. Yours had to be either somewhere between these two. So I should only have one. So I'll use that one. Here's another hydrant. So point. Whoops, point. Center. There's my hydrant. Here's my valve chamber at the intersection. And then here, I got to turn on my existing stuff. Sorry, not there. My existing. So then I would have, I think they're frozen, existing water stuff. And my existing, I think that's it. So now you would see here, there's my valve chamber. Here's where my water main starts. This is the point right here, right? Existing versus proposed. And then I have this T, and then I have this valve chamber. So these are all the things in the plan view, right, that are going to show up in my profile. So I'm going to click on this, right click, select similar. These are all the, whoops, not view. Click, right click, select similar. So these are all the points in the plan that are related to my water main. Valve chamber, hydrant, valve box, hydrant, valve chamber, beginning of new pipe, right? So the plug, the T, which we're going to abandon, but it's there, and then the valve chamber here. So I'm going to take those and I'm going to project them to street A. How do you do that? I'll show you the command, profile view, project. You've done this before, right? Projecting points from plan to profile. We use this technique for modeling our corridor elbows. I'm going to put it here. The elevations are all garbage. So I'm going to use my original ground. I just need the station values. I'll worry about the elevations myself. So it's the stations that are okay, but the elevations. If you use 0, then your grid's going to expand, right? Because it starts at 190. So make sure you bring them in range, same as before. And these are where all those items are in the profile. So I know I have a valve chamber here. We're just going to draw a line here, straight down. I know I have a hydrant here. I know I have a valve box here. Whoops. I know I have a hydrant here. I know I have a valve chamber here. This is the plug. This is the T, which is not going to get used, but there it is. And this is the valve chamber over here. Whoops. And then I'm going to delete these. Select similar. And I'm going to delete them from the profile. So I've marked all of the station locations. So how do you draw each item? Let's start with something simple. Let's look at the valve box. How do we represent a valve box in the profile? Well, let's look at one. Are there any valve boxes on this street? Let's take a look. Do we see any valve boxes of water main? So there's a valve chamber. There's a hydrant. We see any valve boxes? No valve boxes. Okay, let's try Chuchmak. Let's take a look at Chuchmak instead. So if we go to Chuchmak, so how do they represent a valve box? So here's a valve box. There's the plan view, right? We drew all those. We projected the profile. So if we go straight down here, what's a valve box look like? Well, there it is. It's a vertical line with what looks like an X for the valve, and then the label, 200 valve box. So you need to represent that. So how do you do it? Again, these are just tips and tricks. I'm going to show you. You can do it however you like. As long as at the end it looks similar to this. So let me draw this. This is my interpretation of what I see here. Again, it's schematic. Okay, so how do I draw it? Well, I know, again, my valve chamber is here. Let me just double check, make sure I have the right location. So this valve chamber is around station 149, 37. Let's just double check. 149 is over here. Yeah, so this is the valve chamber here. So the valve box, right? Run 149 right here, between 140 and 160. So I've got the right thing. So it goes to the surface. It goes to the surface. So it's trimmed off right here. Trim. I'm going to make a copy of this text, put it on the appropriate layer. My O snaps are causing me grief. So this is a, let me see, 200 diameter V and B. 200 diameter, whoops, percent C, V and B. V and B. Turn it up on its side, 90 degrees. Put it on the appropriate layer. So it would be on the water main pipe profile. There should be a text. So there's a pipe, a profile, water main profile. And there should be a water main profile text. So this layer should have a text version, right? So you always need something and its label. So let's look at that. So the water main, whoops, name, water main. Where's, oh, sorry, existing. Where's all my water main stuff? So C, road, water. So we have a water main profile. Copy, we should have a water main profile txt. I'm going to keep drawing here for now. Okay, so this should be on the txt layer, not the profile layer. And we move it close to the top of the road, right? So that the top now starts to look like this. And now we draw a line down to the middle of the pipe. Let me just isolate the layer so it's easy to see, including the text. Okay, so there it is. You don't need this traced version, right? But I'll keep it for now. You don't need it. So now I'm going to make a copy of this to the middle of the pipe. So I'm going to turn my ortho on. So if that's a 200, then it's going to be 100. 0.1 times 10 is 1 meter. There's the middle of the pipe. Okay, so I'm going to trim it to there. And now I need to draw that X. So pick a number. What does it look like? It looks like it's not quite 90 degrees in there. So I'm just going to use, I'm going to offset, if this is 200, I'm going to go 100 each side, 0.75 each side. So this way and this way, extend to the bottom. And then I'm going to draw a line from this intersection to this intersection, and from this intersection to this intersection. And then I don't need, I'll trim this here, and then I'll trim between these two lines here. And then I don't need the line in the middle, and that looks a lot like what I see here, right? Exactly what I see here. So I drew this vertical line, I put an X there, I draw a valve box, and that's my standard for it. So that's how I draw the valve box. How do you draw a hydrant? Hydrant is right here. How do you draw a hydrant? Well, let's take a look. What's a hydrant look like? Oh, here's a hydrant right here. So instead of an X, it has this circle, and the circle is the size of the pipe that goes to the hydrant. The pipe that goes to the hydrant, I'll show it to you in plan. The pipe that goes to the hydrant, actually we'll look at it here. According to the standard, this pipe here is always a 150 pipe. Okay, doesn't matter what the main is, the pipe that goes to the hydrant is always 150. How do I know? Look at the standard in Halton region. Okay, so I know that's a 150 pipe. So how do I draw that in profile? Well, so I know this is the hydrant. Again, I'm going to make a copy of this straight down 1 meter to the middle of the pipe, and I'm going to draw an ellipse right there. Okay, remember, this is 200. I want a 150. So I'm going to offset 0.075. There's the sides of the ellipse. And then from there, I want to go up 0.75 times 10. So I'm going to make a copy of this. 0.75 times 10 is 0.75. 0.075. So there's the top and then the bottom. So the ellipse fits right in there. Intersection, intersection, intersection. And that's what the pipe would look like coming out. Okay, we'll go back to here, and it's broken. So I'm going to use the same offset. I'm going to draw a line from the center, and I'm going to offset at 0.75, the same gap I'm using on the valve box, right? It's the same gap I'm using here, just to be consistent, and then it breaks the pipe. And we keep this. And then this starts at the top, quad, and that looks a lot like what's happening here. And then it goes up and beyond. It looks like a hydrant. Not really what it looks like, but that's what they've done. And it goes above the ground. So I take this and I bring it way up above. How high above? Well, let's take a look. It's not very high. It looks like about maybe half a meter vertically. So I don't know, copy this straight up, half a meter times 10 is 5, and trim it. Oops. Copy this straight up 5 meters, trim it at the top, and there you go. Now to draw that symbol, you can borrow. You can borrow from the plan view. Make a copy of the hydrant. Circle, oops, circle in 3 lines. And bring it up here. All right, you want to rotate it. So align this from here to here and from here to here. Oops, it's upside down. Rotate it 180. And put this on the center. And then trim it to the bottom. And put it all in the same layer. And that's the hydrant. Now there's text for the hydrant. This is an interesting part, this text. All right, hydrant and valve, OPSD, flange elevation. How do you do all that? Well, again, you make a copy of the text you had before for the valve box. How do you type it in? Well, what is it? Let's take a look. So it's hydrant and valve. Oops. And valve. Oh, sorry. Hydrant and valve. OPSD. What's the OPSD number? 110501, 1105.01. And then there's a flange. Flange elevation. EL dot. And then there's a number, 123.12. And you need to know what that number is. I'll show you how to get it. Right? What's the flange elevation? The flange elevation, if you read the standard in Halton, the flange elevation in Halton is the boulevard elevation, wherever the hydrant is, plus 0.15. Okay, so here's what it looks like in cross section. Right? So if this is your cross section of the road, the hydrant, where the hydrant sits, this is the boulevard elevation. The flange for the hydrant is 6 inches above the finished ground, 0.15 above. Okay, so whatever the elevation is where the hydrant is on the boulevard, add 0.15. So how do we do that? Now we're going to leverage some other stuff that we know. Let's go back to the plan view. So I'm working on the first one from that side. So it's this hydrant here, right? This hydrant here. So I'm going to put not an AutoCAD point. I'm going to erase that. Actually, I can use this. I'm going to use this. That's the spot, right? So now I'm going to go project the points to the object view, this one. Go to the profile right here. Right? It's going to come in here. And then for elevation, I'm going to use the road. And this is in the boulevard of the road. So it'll give me the road elevation. Say OK. And now you'll see it's in the boulevard. Remember, this is the center line of the road. So that's the boulevard elevation. So whatever this elevation is, it's not showing it to me, but whatever this elevation is, I'm going to add 0.15 to it. Okay? Now, the reason you're not getting a number here, because the source elevation is 0. It's in the plan view, it's flat. So it's showing me that. If you want, you can change the style. change the standard style, and again, you can make a copy of it. Right? Create a copy, change the name, hydrant, or whatever, and then change the, instead of the source elevation, use the projected elevation, and change this to projected. Instead of source, use the projected elevation. And then add that, use this little button. So instead of source, it's going to say projected. Say OK, say OK. Change this to the hydrant. And now it's showing me the projected elevation. So that's the elevation on the boulevard. If you don't like that, you can always do it with a point. Watch this. That's one way of doing it. Another way is if you take a point. I'm going to make a copy of this, any point. Make sure that the description is not FG. So change this to something else, ground. Right? It can't be FG, otherwise it's going to screw up your finished ground. Right? Put this right where the hydrant goes, and then elevation from surface, roads. That's the road boulevard elevation. And that should be the projected elevation, 545. If we look at the label that I created, 545. I have to add 6 inches, so it's going to be 195.60. So this elevation is 95.60, 195.60. That's the flange elevation. So whatever the boulevard elevation is at the bottom of the hydrant on the ground, add 6 inches. And that's how you get the flange elevation on your hydrants. And that looks a lot like this. Okay, so that's how you get the elevation. That hydrant, by the way, this one on Chuchmak, right there. Watch, I'll use the same technique. Let's see how good the designer was. So there's a hydrant. Is it here? I'm going to use this one because I think I drew that one manually. I'm going to use this one. If I put a point here, copy. I'm going to use this one here, node, put it here, center. Okay, let's see how close it is. Elevation from surface, use the road. So if I add 6 inches to that, 41 plus 15 should be 56, 556. That's this hydrant over here. 550. So it's off by about 6 centimeters. Okay, but we did change the road profile through here a little bit. Remember, this is now not relative to this road anymore, but it's close. That's how it's done. Okay, so that's the technique. What's the flange elevation? The boulevard elevation of the hydrant plus 6 inches, or 0.15. So you need to do that for all your hydrants. You got to do this 4 times. So that's how you draw a valve box. That's how you draw the hydrant. How do you draw the valve chamber? Right, there's one on this side, valve chamber. Well, that valve chamber, let's look at a similar valve chamber. Let's look at, that's a valve box. Let's look at the valve chamber. I guess we can use this one. What does a valve chamber look like? It looks like a maintenance hole, right? And it's got this cross inside, right? And it just goes up. And it's a little bit tapered, right? It's shown tapered. I'm just going to draw it vertically straight up. And it looks like there's a little bit of a sump, right? Lower than the pipe. So let's take a look at that. So I'm going to draw my valve chamber. Now, see how the road has a crown on it? I would ignore the crown. So this piece here and here, I would ignore. I'm going to trim those off. And then you can go straight across. So you can ignore the crown when you're going through the intersecting road. Okay. The elevation of this actually comes from 1.7 below this road, which is 17. There's really where the top of the water main is, right? Because this is a T intersection. So this water main would be below this center line. So whatever the center line is here, down 1.7, that's the elevation of the top of pipe on this side of the road, technically. Okay, so it's actually a little bit higher. So this and this would shift. Come on. Sorry, going too fast for my own good. These two would shift to here. Right, you would ignore the crown. Okay, That's the water main. So how do I draw this? Well, I'm going to make a copy of this. Typically, the valve chamber, if you remember, the diameter is 1800. So I'm going to offset 0.9 on both sides. There's the inside diameter. Okay, and then from here, I'm going to go down a foot. So 0.3 times 10 is 3. Okay, you could be that deep or 1.5. 1.5 might be more representative. There you go. And then fillet this with this and this with this. And then from the edge of the chamber, I'm going to trim. And then I'm going to draw a line from here to here, from here to here. Draw a line from here to here, and from here to here. And then you get rid of these two, and that looks a lot like that. Okay, so I'm just eyeballing it, right? I'm trying to be standard. I was going to draw the valve chamber on the other side the same way, right? How do you finish it? Well, you need the other half of the road. Remember the cross section of the road? You need the other cross section of the road. So if you didn't draw the other half of the road, you'd have to now, right? As a minimum in here, you would need 2% going the other way, right? And that, whoops. And then extend to the road surface. And that's what the valve chamber would look like on this side. Right, and then really, if you want to complete the picture, you should draw, I'm not going to do it accurately, but you should draw, you know, the boulevard, top, back, a curb, and the 2% line going up to the street line, right? That's not accurate, but that's missing. That should show as well, just to complete the picture. Definitely you need this, otherwise you won't be able to draw the top of the valve chamber. So that's how you do a valve box, that's how you do a valve hydrant, and that's how you do a valve chamber. The last thing I guess to look at is a plug. So if you remember, there's a plug at the beginning, right? So what item did I have, right? I had the 1, 2, the third one in. How do you draw a plug? Again, it's all schematic. So it's not one. I'm going to draw this, isolate this line. Again, I'm going to ignore. I'm going to go from here down 1.7. This is a T intersection, 1.7, which is 17. There's the top of the water main here. So I'm going to ignore the crown of the road and take this all the way across to where the water main is, to where the valve chamber is, sorry. Right, so there's your valve chamber, there's your T, and this is the plug. So what does the plug look like? Well, I'm just going to offset 0.75 on this side. I'm going to make a copy of this, 0.075, maybe more. Copy this up 1 meter, copy this down 1 meter, and then trim it on both sides, and then trim this here and here, and the original line was here. There's what your plug looks like. This on this side should be existing, so now you can break this, whoops, break this, extend both sides to the line, and this should all be existing. Make it white or gray or something, right? So that's the existing pipe, including the plug. That's existing, and that's your connection point. So it's starting to look like a lot like this. Again, if we look at Ledger Way, you might see some interesting stuff too, as existing and proposed interface. So if you look at the connection point here, see the way they're showing existing? It's a dashed line and it's not hatched. And then they're showing the plug. They're drawing the plug backwards, in my opinion. These lines should be on the original pipe, plugging it. So your proposed pipe is hatched. Your existing pipe is dashed, not hatched. Right? So you can look to that. That's how you do existing. So back to the drawing. You can change. You can put this on a different layer, existing, or you could just change the line type directly here and change the line type to hidden or dashed. All right, so that's the existing water main, that's the proposed water main. Now, if you want to hatch it, again, if you want to hatch it, BH for hatch, pick a point and it'll hatch inside. So that's inside, that's inside, that's inside. Oops, this one, And this one, I didn't do the other hydrant and valve chamber here, but you need to do that. And then the hatch they're using is called dots, I believe. Where's dots. And now you have to play with the scale. I would probably make it smaller, 0.2. Right? And it starts to look like this, dots. Right? So if you were to print this, plot, just out of curiosity, if you were going to plot, it's probably AutoCAD, no, window, preview. It starts to look a lot like the stuff that we saw. Right? Valve chamber, hydrant, valve box, and so on. Okay, so just some, again, it's your AutoCAD skills that are going to take you through this process. Okay, don't do any hatching until you draw all the hardware, right? Otherwise, you have to break this again, right? There's going to be a gap here and a gap here, just like these two, right? So don't hatch until that. Hatching is the last thing you do, right? But make sure that you put the text for the hydrant, put the text for the valve, put the text for the valve chamber, label the pipe size. It's a 200 millimeter PVC pipe, and make sure you then hatch the pipe. So that's the technique for watermain. You have to do it here, and you have to do it here. Now on Chuchmak, there's an existing plug. You're actually connecting to this existing plug. So all you need to do is show maybe just a little bit of the existing pipe. You can maybe even not show the hydrant. Don't show the existing hydrant. Just draw some existing pipe and the existing plug, and then everything else inside on street B is proposed, all the way to this street A intersection. So you're going to draw, let me just project that point, sorry. I'll go back. All right, so you're, move this point from center, whoops, from center to end point. That's the beginning of the system, right? So we're going to go project this point. And again, it's just the station you're interested in. You can use that elevation or not, it's up to you. So there's where your hydrant starts, right there. Sorry, not your hydrant, your design. Right, so everything on this side is existing, everything on this side is proposed. And that's where your plug will be. Right, so if you draw your line from here to here, copy it straight down, 1.7 or 17 meters. And then for the size, it's a 2 meters. And if you break this, whoops, break this on either side, and break this on either side, extend to the line, and then you could match the property. It's supposed to look like this over here. Right, and then you can use the same technique I had. Take this straight up 1 meter, take this down 1 meter, offset this 0.75, trim, get rid of this and make it all existing. There's your plug on the water main here. And there's your proposed pipe connecting to it. So you need to show over here. Everything else from there all the way to the end of street B is proposed water main. This is street A, right? So there's going to be a valve chamber here. And it's probably going to be, let's take a look. It's going to be, so storm, and water on the other side, right? So you're going to have your storm, your sand, and your water main is going to end somewhere over here. And don't forget to save your drawing as you go. So that's all. Now, again, when you draw all that, let me remind you again, if you move this, if you move your grid, none of the water main stuff, anything you drafted manually stays exactly where you put it. So be careful about that. Right? Basically, once you start drawing, make an effort not to move this. Leave it where it is. Right? So make sure you've got plenty of room in between the profiles so that you've got a lot of room to work with. Okay, and that's how you draw your water main. So if we go back to the shopping list of stuff, let me see if I can find it again. What I asked you to do. So if we go back to submission 3 requirements, oops, submission 3 tasks. Draw the water main with minimum depth of cover complete with annotations in the profile views of both streets. So all the water main in profile. Make sure you include the valve chambers, the valve boxes, and the hydrants, and the hydrants complete with the annotations in the profile in both street A and B. And for the hydrants, include the flange elevation. There's 4 of them, at least 4, maybe 5, okay? Depending on how many you drew. So that's the water main. Sanitary sewer, update the drainage areas. You should have done that by now. Prepare the design sheet. That's almost an independent exercise, but I need it. Create the pipe network based on minimum cover at the upstream maintenance hole and calculate the inverts on minimum slope and minimum drop starting at the upstream and work your way downhill. Okay, that one's backwards. Sorry, somebody had a question. Did we submit the design sheets? No, I want the Excel sheets. It's on this form here. You'll see. Exactly what's required is on the document. Okay, so prepare the network, draw the sanitary sewer in the profile A and B, complete with labels. Okay, storm sewer, update the storm drainage areas if you haven't already done that. I want to see those again. So I want to see the PDF of the storm drainage and a PDF of the sanitary drainage. So plot the drainage area drawings again. I want to see your areas because I want to be able to relate. What's your area and population on the drawing? What is it on the spreadsheet? Okay, so I'm going to check that. Make sure that you're consistent. Draw the storm sewer and profile, calculate and draw all the rear lot catch basins and leads. Okay, and where required, recalculate the inverts for the road storms from the downstream end to the system, to the roads where the rear lot catch basins need to be updated. Remember that 25.25 diameter. So I explained which pipes need to be flattened and lowered. Okay. If the inverts are still too low, raise the rear lot catch basin leads. So we talked about that. Compromise the cover because we know that concrete encasement is going to fix that. Okay, and then review the proposed sewer crossings, make sure nothing is touching. Okay, now, at the end of the day, believe it or not, and I don't think you've seen this yet, at the end of the day, what you're creating, here's the wow factor. Ready? Can everybody see my drawing? I'm going to isolate the layer for storm pipes and sanitary pipes, right? So here's my 2 systems, right? There's some junk on here that shouldn't be here, but anyway. If I take all my storm sewers, actually, let me do this. Let me take my finished ground. Where's my finished ground surface? Let's do the road surface, just the roads. So I'll bring this back to life. Make sure my tin is on, or is it 0? I forget. C10, I think. Oh, where's my road? Sorry, turn everything back on. Oh, there's my road. So there's my roads. I'm going to pick up my sanitary and storm pipes and maintenance holes. If it'll let me see here. So sanitary pipe, sanitary and storm maintenance hole. Select similar. And my surface, object viewer. Object viewer. So there's my road. Now forget the lots. This doesn't have the lot grading. This just has the storm sewer, sanitary sewer, and the roads. Okay. So if you see here, if you look, you see the maintenance holes? Sanitary in the middle, storm off to the side. Everybody see that? When you're creating this information, after your design's done, what you're really creating is this. Ready? This network of 3D pipes. See that underground? And you can do a quick visual inspection to make sure where the crossings are, which is basically at the street A and B, that nothing is crossing, nothing is in conflict. Okay? So you can see how the road, how the maintenance holes, and how the pipes interact with each other. Okay? The surface is a bit distracting. Let's do it without the surface. So let's just take maintenance holes in the pipes and the maintenance holes in the pipes, select similar. So you're creating this, you don't even know it, object viewer. So here's your sewer systems. And you can see right here, the storm sewer is crossing over the sanitary. It's not in conflict. Everybody see that? See that storm sewer right there? Watch. It's above the sanitary pipe. It's not touching it. So you can check this for conflicts. You can actually see all of your pipe systems. Okay, so you can do all this. So this information is actually being created by just updating. So you're typing in all the inverts and the sizes and the slopes. And then the top of the maintenance hole elevation is coming from the surface for the road and so on. And all of that data is used to draw this in 3D. Okay. Has anybody looked at this in 3D yet? Have you had a chance to look at this in 3D? Anybody? Oops. Yeah, okay, so you have looked at it in 3D. So that's another tool, a visual tool, right? Now there's actually some software that actually does clash detection. It checks to see if two pipes are one inside the other, or if they're too close, that you can actually define a minimum clearance, make sure the pipes are at least a foot apart vertically or half a meter apart vertically and so on. So there's some clash detection analysis you can do. I'm not going to waste your time with that, but there's a lot of stuff you can do, but it's all based on that visual, on that 3D pipe network. You can check them against each other. Okay, so that's really what's happening in the background, what you're creating, and you don't even know it. That's usually the wow factor, right? Seeing the pipes in 3D. So I hope you can appreciate that's what's happening. Okay, I wouldn't, you could look at it at any time, but really it's the finished design that you want to compare, right? Are there any pipes in conflict? Any questions about what we talked about so far? Let me go back to my list. All right, so here's the submission requirement. Oh, and don't forget to lay out the road catch basins. Remember, draw a catch basin at the low points, figure out where the high points are. I did this last time. And then figure out how many catch basins you need between along the gutters, right? No more than 90 meters apart. Make sure you draw your catch basins. When you draw your catch basins, make sure that they're not in a driveway or going through a pipe. I'll be looking for that, right? So put the catch basins in a spot that makes sense, not in a driveway and not through a sanitary or water service pipe. How to create the basin at the second elbow. What do you mean? How do you create it? You can unmute yourself, Trong, if you want. You want to know how to create this catch basin? How to draw it and plan? Okay, so I'm going to turn this off. I'm going to delete this. Okay, so how do I draw this catch basin? So let me turn off all the distractions here. Not sure I understand the question. The front catch basin. The front catch basin. The road? You talking about the roads? Yeah, I did that last week. You're talking about these ones? The ones on the road? You're talking about the road catch basins. These ones, this one here and this one here? Trong, I'm not sure I understand the question. The one at the elbow. Can you unmute yourself and ask me the question? I'm not sure I understand. There are none at the elbow.
Sorry, it's me, Trong.
Yeah, go ahead.
Yeah, so as per the catch basin on the street, so I see, so last week you showed us how to draw the catch basin on the elbow in the intersection between street A and B, but I don't know how to create that one on the elbow street B. Would it be the same thing? Because the low point, yeah, because there's a low point there, right? So there should be one catch basin.
There's no low point here. There's no low point here. There's a high point here, and then there's a low point here. So that's the beginning, right? You need to know where your low point is, and you need to know where your high point is. So now between here and here on both sides of the road, you need catch basins at least no more than 90 meters apart. Right?
Yeah.
So if I draw a line here, endpoint, and I draw a line here, endpoint, I'm just going to make a copy of this. Okay, I'm going to just make a copy of this stuff here, including this. I'm just going to do this side of the road. It's the same on the outside. Right? So here's the low point location. Here's the high point location. Let me trim off everything else. Right? And then I'm going to polyline edit, join these. Join, 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 join. So this is one polyline. This is the low point. There's a catch basin here. This is a high point. There's no catch basin here. So now I need to go in between 90 meters. You're talking about the measure command that I used? Tron?
Yep. Can you show it again, please?
Yeah, so measure. So I'm going to use the measure command. I'm going to start at this end. Doesn't matter, but I'm going to start at this end, and I'm going to go every 90 meters, 90. And it's going to put a point on the polyline, measuring every 90 meters. So the distance from here all the way to here is 90 meters. The distance from here to here is 90 meters. And then if this is 90 or less, it'll show it. Okay. So if I draw a line from this node and this node, if I trim, this is exactly 90 because I started at this end, exactly 90. This distance from here to here is exactly 90, and then this leftover piece is 90 or less, right? So if I list this, it's less than 90, 74. Okay? So that's one way. So my first catch basin, right? My first catch basin, if there's a catch basin here, the next catch basin can't go past this point. It has to be there or to the left, to the right. Okay, so that's why I put a catch basin somewhere over here. I could put one on this side, but not on this side. Otherwise, it's more than 90 meters. Same thing here. Once I put this one in, so once I decide where this goes, if I move it over, then I'll have to shift this one over 90, so it's not more than 90 meters. Right, so I'm going to put my catch basin. So let me just move these. I'm going to move these markers from this end point. I'm going to put it back on the street here, end point. So there's those two markers. So I put one catch basin here. That's less than 90 meters. And then between this catch basin and this catch basin, I'm going to measure again. Make sure it's 90 meters. I'm going to draw a circle because it's on a straight line. 90 meters. The next catch basin has to be inside the circle. And there it is, just by a little bit. And then you have to check the distance between this catch basin and this high point is less than 90 meters. All right, so you can make a copy of the catch basin, the pipe, the gutter, and just do the geometry off to the side. All right, I'm going to draw a line from this midpoint, trim it off here. I don't even need the catch basin anymore. And then here, trim it off here. And then polyline edit. Take this, yes, yes, and join all these pieces. This has to be less than 90 meters. 86, good enough, and so on. So I know between here, between this low point and this high point on this outside turn, I need at least two catch basins. And where exactly do they go? As long as the distance between the catch basins is 90 meters or less. And you can treat the high point as if it's a catch basin, right? 90 meters from here. I could do this measure command. I could do the measure command from either end, right? I could start here and go uphill 90 meters, or I could start here and go down 90 meters. Right, so now from here, this is 90 meters. From here to here is 90 meters. And now from here all the way to here is less than 90. So the catch basins are going to be somewhere between these 2 points and these 2 points, approximately. But I need two more catch basins. Because the total distance, if you take this distance, 254, copy, and you do a calculation, 254 divided by 90 tells you how many spaces. There's 3 spaces. That rounds up to 3, so I need two more catch basins so that I have 3 spaces. A space here, a space here, and a space here. Does that answer your question, Tron? Now, when you place the catch basin, once you decide where the catch basin goes and plan based on it, make sure that the catch basin is never on top of a pipe, water main pipe or a sanitary pipe, or never inside the driveway. You don't want to drive over this if you can avoid it. So always between sanitary and water, and always between driveways. Okay, whoops. So never put the catch basin on a pipe, water main, on a sanitary water main, or in the driveway. How did you calculate? Oh, okay, yeah, Daniel, we'll get to that question. Yeah, thanks for reminding me. Okay, Tron, does that answer your question?
So I just have one last question. So for the one at the intersection between street A and B, the one at the low point, I remember. So why is it placed on the west curve of street B instead of the east curve? Because the catch basin lead had to cross the road and connect to the manhole.
Talking about this one?
Yeah.
This one?
Yeah, that one.
So I know there's a low point here on this gutter, right? So I have to connect this catch basin to a sewer, and this is the closest sewer.
Yeah, good. So we have to draw it, and so why is not placed in on the street A? Would it be closer?
Because there's no sewer on street B.
Yep.
So remember your drainage areas. Even your drainage areas indicates this much. Right. This area. This area all drains to that pipe. So does this area. This sanitary storm. But anyway, the water coming from the high point to here and from the high point to here gets into that catch basin and it goes out this sewer right here. So you have to connect this low point to this sewer. Does that answer your question, Tron?
Yes, that makes sense. Thanks.
Okay. Okay, does it matter if the catch basin is on the rear lot catch basin? Does it matter? Yeah, that's a problem. You can't put a pipe through the catch basin lead. No. So sorry, you have to avoid this pipe as well. You can't put a catch basin on top of a pipe. So avoid the water service, avoid the sanitary service, avoid the rear lot catch basins. Yeah, good question. Okay, so sorry, Daniel. Where's Daniel? I want to get back to Daniel's question. Okay, so how do you calculate that? Okay, so there is a sheet. Let me see if I can find it. I can't remember. I know Professor Neruzzi. Oh, sorry. So let's just finish this. So this is what you have to hand in. Both drawings, even though we didn't change the topo, both DWGs, a PDF of the drainage area plan again, a PDF of the storm drainage plan again, and I want your Excel sheets for both designs, sanitary and storm. Give me the Excel sheet. Okay, so I'm going to check your calculations as well. Right, so that's the submission requirement. 2 DWGs, 2 PDFs, 2 Excel sheets. All right, so let me just check here a minute. Let me see if I can find this file for you, Daniel, and I'll do that calculation. Is it the same PDF? Yeah, it's the same PDF, but it's going to have all the information now, right? It's going to show all your pipe sizes and slopes, all your maintenance hole numbers. It's a complete drainage area plan now. Right, so it's not just the areas, but you'll see all the complete design, all the labels for pipes and maintenance holes for both systems. Yeah, it's a final version. The first time I looked at it, I was just checking the areas you drew and the bubble data, but now you use that to create your sizes and slopes. So now that should be included. Yeah. Claire, go ahead. I'm looking for something for Daniel. Go ahead. You want to ask a question? Claire?
Oh, okay.
Yeah, go ahead.
Yeah, my question is about the pointer, the SB point or SW pointer. Sorry.
Oh, the swale.
Yeah, the swale point.
Points. Yeah.
It's on the lot 6. They have 2 points, but I don't know how to decide the where to put these 2 points. Lot 6.
Oh yeah. Okay, hang on. Let me just bring that up.
Mm-hmm.
Share application, entire screen. Can you see my screen?
Yes.
Yeah. Okay, so where to put these 2 points?
Yeah.
Okay, those 2 points, you'll notice this is the high point. Right, yeah. So 38 flows to 411, and then this flows all from 7 all the way to 6.
Yeah.
So it doesn't really matter where you put them, just 2 interpolated points. Right? If you want to calculate them, based on the rise, you can calculate the run.
Okay.
You know this elevation? That's the rise. You can calculate the run based on the slope between this point and this point.
Okay, interpolation then just. Okay.
Yeah, just show me 2 points. Yeah, and I
Okay.
think they're right across. They're right across. Let me just check. They're right across from the existing ones. Watch. I think strategically, I chose them. Hang on a second.
Okay.
Regen. Yeah, let me just take a look. They're actually opposite. And maybe I should have mentioned this before. That's a good question. They're actually opposite the points that you imported. Remember the imported points?
Uh-huh.
You remember around the perimeter?
Yes.
You imported all these points?
Yeah.
So there's 2 points there. They're directly opposite. So they're perpendicular. So if you offset 1 meter.
1 meter, just all.
Yeah. And then approximately 1 meter, and then they're perpendicular. Yeah. So it's right opposite these 2 points.
Oh,
yeah.
okay.
Good question.
Perpendicular. Okay. Thank you.
Yeah. Okay.
Another one is about the. I also have a question about the calculation. It's about the sanitary, because we don't discuss about the sanitary actual flow at during the class.
How to calculate the actual velocity?
Yeah. Can you go to the?
That's Daniel's question. That's what I'm going to do next.
Same.
Let me just find the file in it. Yeah.
Okay. Sure.
I'm just trying to find the file that Professor Neruzzi gave you. Okay, so here's. So you need. So let me share this. Hang on.
Thank you. Okay. Thank you.
Yeah, you're welcome. You're welcome. So let me show this. Where is it here? Okay, Daniel, this is it. I'm finally getting to it. Sorry. Claire had the same question. So you remember this document that Professor Neruzzi gave you from last year? I think he posted it again this year. Do you all have a copy of this? Okay, so you have this. Okay. So not the first page, but the very last page. This thing here. This is how you calculate V full, V actual. Okay, so let me do one. We'll do one together. Now this table is different than the one I'm using in my spreadsheet. Okay, so let's look at. I'll do V. So for sanitary. So let me open up my sanitary sheet. So my sanitary sheet is on my desktop. Sorry. Sanitary. Okay, so how do we calculate V actual? Okay, so you're not going to get these exact numbers because I'm using a different table. Okay, so my table looks like this. My table, is it on here? Yeah, so see my table? It's much bigger than the one you're using, but it's the same idea. Okay, so I'll do the calculation, and then you'll see my numbers have a lot more decimal places than what you're using. Okay, but let's go through the calculation. So if we go to Chuchmak, so let's look at Chuchmak. So what you need to do is first you look at V. So if you look at the table, right? If you look at the table, first you need to look at the diameter of the flow. So the first column you don't need. You look at the middle 2 columns. Okay. So first you need to calculate QA divided by Q full. Q actual divided by Q full. That's the second column. And then V, and then you're going to get V actual divided by V full. Okay, so let's look at this, the first one. So we calculate the total flow, right? There's the total flow. And this is the actual. And this is the capacity of the pipe full, right? So this one is actual and this one is full. So if we look at Q actual divided by Q full, we're going to get 0.0014 divided by 0.033. Okay, so let me show you my camera. Right? So we take the actual flow divided by the full flow. Actual flow, full flow. And we look at this number. So let's do the math. 0.0014 divided by 0.033. And we end up with a number 0.04242, and it goes on forever. Okay, that's the number. Now you got to find that in the column of V actual equals V actual divided by V full. So let's go to that sheet. So in this column, we need to find that value, the closest one. So if you zoom in here, you'll see this one here, 421. That's the closest number. Okay, so when you find the closest number to what we just calculated, you read this number here. Okay, so now V actual divided by V full is 4953. So according to this, 4953, 0.4953. So I go back to my camera, sorry. So V actual divided by V full is this number, 4953. Right, so now I know that relationship. Well, V actual is equal to, if I cross multiply, 0.4953 times V full. And that's how you calculate V actual. So what's V full? Let's go back to the spreadsheet. We calculated V full, it's 104. So V actual is 104. So this is equal to 1.04. So do the math. V actual is equal to 0.4953 times 1.04, and that equals 0.4953 times 1.04 is 0.52. And if you look at it, I'm actually getting the same number, even though I'm using a different set of values. So my values are a little different than yours, right? So if I want to find 4.2, I'm way down here. 4.2, 4.2, 4.2. It's going to be somewhere in here. And then I'm going to use this. Sorry, somewhere in here. 0.042. Sorry, 0.42. 0.42. So there's my number. I've got a lot more decimal places than you do. And this has a lot more decimal places. So mine is a little more accurate, but it's the same concept. Same concept. Okay. Now, again, using this one, what Professor Neruzzi gave you is good enough, right? So using this table will do it for you, but you really only need to worry about these two middle columns, right? It's basically one equation with one unknown. You know these two numbers. You know both of these, Q actual and Q full. And over here, you know V full and calculate V actual based on this relationship. So you find Q actual divided by Q full in this column, and then you just look next door. If this is the number, then this is true. And if that's equal to this, you already have V full, calculate V actual. And that's the calculation. Yeah, you might not get, like when you're trying to reproduce the values on the spreadsheet, they might be off a little bit because this table, if you're using this table versus the one I'm using on the spreadsheet, you might get a slightly different result, but the technique is the same. I just have a little more accurate data, that's all. Okay. Should we linearly interpolate the value? You could if you wanted to. You could, but what I would do is I would probably take the higher values. If you're in between two numbers, I would take the if it's close, within a decimal place, I would use it. But if let's say you're exactly in between two numbers, I would use the higher number. I would assume that the V actual is a little bit higher, which is conservative. So, instead of wasting your time by interpolating, you could just, pick one of the. I don't think it's going to make that big a difference. Right? It'll be close. You'll notice, though, when you do your sanitary calculations, and this is true of the sanitary calculations, it's very, very difficult. This is mine at a glance. It's very, very difficult to get 0.6. You don't get past 0.6 until you accumulate quite a bit of flow. Okay, so you have to kind of keep that in mind. All right, any other questions? So that pretty much takes us to the end of the design discussion. Right, that's all the design. There's a lot more to do in design, but we haven't got 5 semesters just in my course, obviously. There's a lot more to it, but these are the basics. most of what I taught you is the type of effort that you would put in to do a first submission, right? Then when you get your comments back and maybe some more information, you might change some stuff, or you might add some detail that I haven't discussed. Okay, we will discuss some information that you show on the drawing that is just kind of traditionally shown. So we'll talk about this during the drafting, which we will start discussing next week, what to show on the drawing and why. But for the most part, I would say like more than 90% of the design is complete, right? Now it's mostly presentation. Okay. The one thing we didn't do is size the water main, right? We just assumed it's going to be a 200. We would have to analyze it. And again, we just don't have time for it. We would analyze it using a hydraulic analysis, some software, where we would digitize the system and then, put in some flow data, pump curve data. It goes back to your hydraulics stuff that you learned. And then verify that the pipe is actually big enough, or if it's too big. So what that software analysis does, this is worth discussing actually very quickly. We have a little bit of time. So there are operating parameters. Let me see if I can find it here. So if you look at your, let me just find it here. If you go to your, if you go to Halton standards for the design, so if we go to, let me just see the water main design, it's going to tell you operating pressures. Where are they now? Pressure. So the pressure in case any localized area has working pressure in excess of 550 kilopascals, pressure reducing valve. Okay, so the maximum is 550. Okay, and the minimum is 140 under fire flow. So here's what happens. I'm going to discuss the analysis without actually doing it. Okay, I don't have the software, but this is what you need to do based on these two parameters: maximum 550, 140 minimum. So here's what that looks like. So here's our subdivision. Okay, here's our subdivision. Right, here's our subdivision. Inside our subdivision, I think we have 5 hydrants, right? We have a hydrant on street A, 2 on street A, and I think we have 1, 2, 3 on street B. So these are hydrants, right? These are the hydrants on the road. So just like the sanitary system, the water that goes into your house is the wastewater that goes out. They assume every drop that goes in the house is the same water, albeit it's going to be dirty, that comes out of the house. So there's kind of I don't want to say a law of conservation of water, but generally that's what happens. So the water that comes in through your water main goes out through your sanitary drain. So the way you calculate water use, right, is the same calculation you use for water demand. Okay, it's based on population, it's based on peak flows, it's based on minimum use per person, and it's based on a little bit of infiltration, right? A little bit. It's actually exfiltration. Some water leaks out of the water main sometimes, but that's another story. So so we kind of delineate drainage areas on each hydrant, kind of like this, right? And you'd have a population in each area, right? So the drainage areas would look similar to the sanitary population, and we calculate a required flow. Then, based on some flow data, right? So we have a source of water, and we have a pressure that we can translate into a pump data. All this information is used to charge the system, right? So our water main looks like this, right? So once we charge the system with water, the analysis it does is, okay, when there's no fire, there's going to be a maximum pressure of 550 kilopascals, right? So under no fire scenario, you look at the pressure at each point in the system. And remember, the pressure at each point also depends on the elevation, right? Because if you remember some of the stuff you might have done in hydraulics, right? If you have a pipe that's got a slope with a tower, right? If you have a tower full of water, right? The pressure down below, there's a lot of head acting, right? The pressure down here is going to be higher than the pressure up here, right? So the elevation has a role to play as well. So you have to know the elevation at all the hydrants, and then you charge the system with a pump curve based on the system you're a part of, right? You're connecting to this existing one and this existing one. And then during normal operation, you cannot exceed 550 kilopascals of pressure at each node. So no fire. Make sure that none of the nodes, none of the hydrants have a pressure higher than 550. If it's higher than 550, then you might want to consider changing some of the pipe sizes. Typically, you have to make the pipes bigger. Okay? Then what it does is it systematically goes through your model and assumes there's a fire flow at each hydrant. So when you start to draw fire flow on each hydrant, the pressure in the system drops, goes down. So if there's a fire happening here, make sure that you have at least 140 kilopascals pressure at all the other locations. So model a fire here. What's happening 1, 2, 3 at these 4 locations? Are these all greater than 140? If so, it's good. Then it goes to the next hydrant. Let's say you're drawing a fire flow here. What happens to the pressure at the other locations? Are they all greater than 140? Yes, then it works. And it goes through one at a time, assuming a flow at each hydrant and checking the pressure at all the other locations. And it'll go through, if there's 5 hydrants, there's 5 scenarios to analyze. If there's 100 hydrants, it goes through 100 scenarios and so on. And it'll actually, when you use the software, it'll actually show you which pipe needs to be either made smaller if there's not enough pressure, or needs to be made bigger under no fire flow based on the maximum pressure. But the operating range is here. Typically at maximum or close to the higher pressures at your house when there's no fire, typical day. And then if there's a fire, then you still want domestic water flow to each unit or to each point on the system. So you want to make sure that nothing drops below. So that when there's no fire, everything is below 550. When there's a fire, everything is still above 140. And that's the general analysis that happens. And there's a software to do it. You do not design the size of the water main directly. You really do what we did. We assume a size and then we analyze it. And if it doesn't work, then we change the pipe sizes, either up or down depending on the pressure. And that's basically how it's done. Okay, without getting into the details of the calculations, that's the general idea of the analysis that takes place. Okay, I think in my career, I think I've only ever done about 3 or 4 of those. Usually we kind of assume some sizes based on typical, and then I found we had a different department that actually worked on larger water mains that was able to analyze that for us. So we would do our design, send it for analysis, and they would say, yeah, it works, you're good. Or, no, you need to maybe make some sizes either bigger or smaller. So they would send you the result, and then you would see which pipes potentially need to change, and then you would change it. You'd update your design, and then you'd send it out for analysis again, or do the analysis yourself, depending on who has responsibility for the water main analysis. Okay? So like I said, in my career, I've designed a lot of subdivisions, but I think on the subdivisions I worked on, based on my detailed design responsibilities, the water main analysis was typically left to a different department in the companies I worked for. Okay? So I've done it a few times, but I'm no expert. I understand it, but I'm no expert myself. So, but it might be something you get involved in or start to do. Okay. Typically, that analysis is done at a very large scale. So a small subdivision like this, they might have already done this scenario as part of a bigger development, right? And they don't even have to run the analysis. They'll just tell you, yeah, those are the pipes we assumed we're going to go there anyway. So anyway, it's something you need to check. So if you don't do the analysis yourself, you need to find out who did it, whether it was in your office or a separate company, or maybe the municipality's already done an analysis, so you can look at that information. Right? So that's the water main analysis. So at this point, we're just assuming the size for analysis. We haven't done the analysis. Any other questions? Remember, this is due Friday. This is your last submission, the last design submission. After this, all that's left to do is drafting one plan profile and one grading plan together with a cost estimate. Next week, we're going to look at cost estimates. What was the there's a few. I've used one called Water Gems, GEMS. There's also a HydroCAD. There's a WaterCAD. There's a few different software. I think AutoCAD has an add-on that does it as well, but I've never used the AutoCAD version. So there's a few softwares there. So here, I'll type here, WaterCAD. WaterCAD, HydroCAD, what's the other one? WaterGem. These are a few. Some of them you might actually have access to. I think because you know the fire protection people, you know the other fire program at Seneca, they design sprinkler systems. So they actually use, I can't remember the name of the software, but they use a hydraulic analysis to design their sprinkler systems. Because a sprinkler system inside a building is just a small version of a water main outside on the road. So they have to be concerned with pressure and so on. So they actually do fire flow analysis inside buildings, but the software can be used for any size pipes. So you can use it for outside as well. The analysis is the same. Yeah. All right, so that's it for today. That's the final discussion. Please pay attention to the submission requirements. I'm going to show them one more time. Right, make sure that you hand in everything. All right, and remember, you want to make sure everything is uploaded and submit everything at one time. Right, if you submit one at a time, I'll only see the one file. Right, so make sure you submit everything together. Okay, so basically finish the design, all the design requirements. And then for the cost estimate, I'll show you a lot of tips and tricks on how to get quantities from the AutoCAD model you just created, right? Some of it's Civil 3D, a lot of it is just AutoCAD. Counting stuff on screen, measuring total length of stuff, and so on. So we'll look at that together. How to do an earthworks analysis, we're going to review that. So I'll show you how to get areas of stuff and how to calculate areas, and I'll show you some how much topsoil you're going to remove, how much topsoil you're going to reuse on the site, how to calculate these volumes, and so on. So we'll get into all this next week, and then we'll talk about the drafting. A lot of the drafting is done. It's just a matter of setting up your plan profile sheet, your grading plan sheet, and then maybe adding a few things. I'll discuss things that are supposed to be on the drawing, but I'm not going to ask you to do them, right? So we'll review the drawings together. For instance, Ledger Way, if we look at, not Ledger Way, Cheechmark, there's stuff on the drawing that we're not going to draw. Like if you look here, see how they're asking for a 1.8 meter, see this, 1.8 meter, 1.8 meter easement. I'm going to ask you to draw the easement, okay? But it's something that usually goes on the drawing. You know, the dimensions for the right of way. They should be on the drawing, but I'm not going to waste your time. Oh, I'm not sharing. Sorry. Thanks. So I do that sometimes. Where's Cheechmark? Let's see. Okay, here we go. Yeah, so if you look at the drawing, right, it shows this 1.8 meter storm sewer, these dashed lines on both sides of the easement. It's on the drawing. I just want to make you aware, but I'm not going to ask you to do that. If you look at a grading plan, there's a lot more in the grading plan that I'm going to ask you to do. So if we look at a grading plan, okay, so let's zoom in on one of these areas. Look at Cheechmark since we're familiar with it, or we're here somewhere. So if you look at the grading plan, you'll see the slope 2%, right here 2%, 2.1%, 2.1%. These, I'm going to tell you it's a requirement on the drawing. I'm not going to ask you to do that. I'll show you how to, but I'm not going to ask you to do that. These bubbles, see this ellipse, this value in the ellipse? I'll explain what it is, but I'm not going to ask you to do it. What else is there? The standard says you're supposed to show the existing ground elevation at all four corners. They didn't do it either, and I'm not going to do it either, so on. So you have to read the requirements of what needs to be shown and what's not going to be shown. The building envelope, you can see the building envelope here. This is your front setback. This is your rear setback. These are your side yard setbacks. I'm not going to ask you to draw those. Okay, but you can see it's on the drawing. So this is more complete than what I'm going to ask you to do. So I'll discuss these requirements, but some of the stuff I'm not going to ask you. So there'll be a list of what needs to be on the drawing and what doesn't. But we will discuss a lot of it, even though I'm not going to ask you to do it. So I need you to know, right? You need to be aware, but I'm not going to I'm not going to ask you to do it. It's getting pretty tight with time now, so I don't want to burden you with too much information. Okay, but I want you to be aware of it. You don't want to be ignorant to the fact when you go to work. Okay. All right. Do we need the slope icon for our swales? No, just put the numbers in. Again, those are things I'm not going to waste your time with. I'll show you how to do it, but I'm not going to ask you to do it. Okay, so there's some techniques there. There's some Civil 3D techniques, but it's a lot of work, and it's a lot in the sense that you have to create some styles, which I haven't provided. So, but I'll explain the technique so that you're aware. Right. So even if you don't do it, knowing it needs to be done is at least gives you an awareness so that you explore that when you start working. If you get a job in municipal design, you're going to learn a lot more than what I taught you. But I've given you a pretty good fundamental. So, all right. So if there's no other questions, that's it for today. I'll see you on Tuesday next week. And in the meantime, don't forget the submission is due Friday. I'm going to send a reminder email probably tomorrow or Thursday. And that'll be it for the design. You're welcome. You're welcome. I'm going to stop recording now.